Yes, I'm going to be talking today about generation of light, generation of entanglement, and I'm going to address well, 3 topics. So first, I'm going to give you a really brief overview of our efforts to make an effective and efficient source of entangled photon pairs. And after that, I'm going to introduce a device, which is novel, and it's very, very promising device for collection of pairs of photons emitted by semiconductor quantum dots. And at the end, I'm going to tell you something about a novel method to characterize the entanglement, which is, as you will see, rather important for us. So to start, let me tell you a little bit why we study quantum dots. So they're very interesting systems, and they have 2 very important functionalities that are first and foremost related to the photon statistics. So they are atom-like systems, so that you can drive them coherently and resonantly, which means that you can induce Rabi oscillations. And to back this claim, and I hope this is... Now, I hoped wrong. I should have looked where there's this little light. And I locked the computer. Total success. Here's the laser. Good. So now we can resonantly excite the quantum dot. And so I wanted to back the claim and show you this Rabi oscillation. What you can see here, this is a signal that we got from a resonantly excited quantum dot. It's a bi-exciton emission of resonantly excited quantum dot. And what you can see on the x-axis is the laser pulse area. What we do here is we actually vary the intensity of the pulse. And this, when we just bring it from the lab, is actually square root of the power. And what you can see on the y-axis is the emission probability. And you can see here that this is an emission probability of 0.9. So what I know, I didn't press anything. I swear. It was a cable, okay. So finally, I come to the point where I tell you this lovely number. And so I know that we had 80 megahertz laser. So 90% probability is 72 million photon pairs. So this is a lot. And another property, very important property of quantum dots, is that we have here photon statistics that is very favorable. It's very sub-Poissonian and anti-bunched. And also to back this claim, here is an autocorrelation measurement. It's performed actually on the same signal as this Rabi oscillation. And you can see here that at the 0 delay, there is almost nothing. So if we for a second forget that you can't actually say anything about the efficiency using the G2 measurement, this is the best you can get to an ideal single photon source. So apart from generating photons, quantum dots can also give you entangled photon pairs. And majority of the schemes that are related to generation of bipartite entanglement, so I'm not talking here about cluster states, this is something different and generated in a different way. But if we talk about the bipartite entanglement, then it is generally related to the existence of the bi-exciton, or 2 electron hole pairs trapped in the quantum dot potential. So a quantum dot that is in a bi-exciton state then relaxes to the ground state down one of these 2 cascades. We call them here I have labeled them as an H and a V cascade. These 2 cascades, they give you photons with orthogonal linear polarization. And if you do not have this splitting here, fine structure splitting, then you're going to get by default polarization entangled photon pairs. We usually do not measure polarization. We measure sometimes, but not so often. We are focusing on generation of time-bin entanglement. And to generate time-bin entanglement, you need to use interferometers, and you need to engineer the probability amplitude for excitation of the system by 2 pulses, the so-called early and the late pulse. And if you can get this probability amplitude to interfere, then with a little bit of post-selection, you can get a state of this form, where here, what you can see is the phase of the interferometer. Why we're interested in generation of time-bin entanglement is that, first and foremost, you do not need to close the fine structure splitting. So this S can be whatever value you would like. And secondly, this encoding, the time-bin encoding, it's compatible with the distribution of entanglement in optical fibers. Actually, it is the type of entanglement that you're going to use for optical fibers. So just to be able to give a motivation for the third part of the talk, let me tell you something about how we characterize entanglement. So usually when you work with quantum dots, you will do full state tomography. And what you can see here, this is a density matrix of a time-been entangled photon state. This is the real and an imaginary part. And then what we usually look at, I'm a bigger fan of concurrence than of fidelity, but the community asks for fidelity, so I like to give them both numbers. You will read out the concurrence of the fidelity of your entangled state. And this is the way how we estimate the entanglement in majority of our works where we studied time-been entanglement, also the polarization one. And a little note on the implementation. I said the time-been entanglement needs interferometers. It needs an interferometer to be generated, and then needs 1 interferometer per qubit. And if you would like to know how this works, we usually work with this triple interferometer, because at the moment we're just measuring bipartite entanglement, so we don't need more interferometers. And we have put our laser interferometer and our single photon interferometers all in one single bulk laser. And this is good, because we don't need to stabilize this interferometer. However it drifts, all of these interferometers, they drift together, so their relative phase doesn't change so much. So we can measure for hours without active stabilization. And this is the method that we used at majority of our works. So this brings me to the second part of my talk. So I have told you that we get these beautiful 72 million photon pairs. Well, there's one thing that I didn't tell you about this. Well, if you have just a quantum dot that is embedded in semiconductor material, due to the total internal refraction, you're not going to get more than 1% of these photons to leave the semiconductor material and to be directed toward your collection optics. So common way to mend this problem is to place quantum dots is what is called engineered photonic environment. So something that's going to help you mediate this transition between the semiconductor material and the air. And this is a problem that is pretty well solved, for example, for extraction of single photons. But when it comes to extraction of photon pairs, it's a little bit more complicated. And to kind of tell you why, let's look at this emission spectrum. So here we have the exciton of a quantum dot. Here we have a bi-exciton of a quantum dot. This is a laser scattering. This is an emission spectrum that we got in so-called 2-photon resonant excitation. And this is what you will see if you look in the total spectrum of a quantum dot when you drive it to get these 72 million photon pairs. What you can observe here, that between exciton and a bi-exciton, there is quite a difference in wavelength, and this is so-called bi-exciton binding energy. It is always there, and we actually like that it's there, because then we can drive the bi-exciton state with 2-photon transition from the ground state, so the laser scattering is here in between the lines. It doesn't mix with your emission. However, it becomes a little problem. If we want to collect these photon pairs, we need to have a solution that is broadband. So we have worked on this for quite some time. Actually, I can not really find someone who has tried more different devices. So we started with the nanowires. We have also tried out the circular Bragg grating cavities or bullseyes. We also did this funny taper. So here down you have a cavity, and this is a taper. This structure has a very popular name. It's called a beer glass cavity. It's very popular on Twitter. And here you have what we call the self-assembled cavities that always form themselves above the site of formation of a quantum dot. But today I'm going to talk about this specific device, which is the low-Q micropillar. And what is special about the low-Q micropillar is you usually do not make micropillars to be low-Q. Usually, the micropillar is going to be made with a moderate to high Q factor, and these serve for extraction of single photons. So when you see these near unity efficiency sources of single photons, are these, for example, there are very popular source, for example, the boson sampling experiment that John Weipan did. We're talking about quantum dots that are in micropillars, and those are these moderate Q factor micropillars. And the way how they work is that they rely on the existence of the Purcell factor. However, in order to get this Purcell factor, you have to limit the line width. So the line width of 0.5 nanometers would be not enough for us. And it has been long believed that if you now start to increase the line width of the cavity, you will lose the Purcell factor, and you will deteriorate the performance of the micropillar. And this is not really true. Here, the figure of merit is this beta factor. The beta factor is the ratio between the amount of light that you couple into your cavity to the total emission. And so if you want your cavity to mediate all your light, you will have to have the beta factor of 1. And usually, you will find this formula here with a factor of 1, because the device is meant to work only on the principle of the high Purcell factor. However, this here is not 1, because when you place not me, sorry. Okay, when you place a micropillar, whatever is not any more resonant or micropillar, it's not going to have the same emission as in a bulk. It's going to get suppressed. So the first thing that we did here, we have did a simulation. I'll show you this on the next slide. But the device that we wanted to investigate is this one here, which is a low Q design. It's a low Q from 200 to 300, 5 microampere on the top, 18 on the bottom. Average line width is around 5 nanometers, 4 to 5. And we have looked at the different pillar diameters. I will tell you in a moment why the pillar diameter is important. So what I have to tell you that these micropillars, they were placed during this hyperspectral imaging, which means that they were fabricated at the site of formation of a quantum dot. But since we already start with a microcavity before the fabrication, we have excellent signal for the alignment. So the precision with which these micropillars can be placed is something less than 30 nanometers. So what we did in the simulation, we discovered that the beta factor can still be big. And the reason for that is this suppression of the modes that are not resonant to the cavity. What we have also noticed that apart from very high beta, which we observe at certain places, we can also see a very low beta. And it all depends on the micropillar diameter. So what happens with the micropillar diameter, you can see here. So in black, you have a transmission mode to the top of the device. So here, at around 910, this is a fundamental mode of the cavity. This is a higher order mode. And this red line is what we call the side mode. It's the light that is literally going to leave through the sides of the pillar. And here, on the top, I'm showing you the pillar diameter. So now, if we change the pillar diameter, you will see that this side mode can become resonant with your fundamental mode. And if we look at the micropillar diameter, you will see that this is a point of the low beta factor, because the light actually, it works similar like a beam splitter. You change the phase condition in a micropillar and decides, oh, I'm not going to go through the top, but I'm going to split. I'm going to go sides to the top. And then you change the phase interference conditions inside, and the light decides, okay, then I'm going to just go to the top. Because if you start to increase, Tatiana, it wants to kill itself. No. Please don't restart it. Thank you. This is a lot of dynamics today. So if we increase the pillar diameter, this mode will go away. And this is how it's going to continue. So when you get to 1.75, again, you have a high beta. So we studied a lot of devices, and I'm going to just focus on two and show you these two. One of those has, shall I say, good diameter, 2.02. And another one has, shall I say, not so good diameter. And in addition, the quantum dot is very off-resonant to the cavity, while in this one here, we have a quantum dot where the exciton and the bi-exciton line lay inside the cavity. So what you can see, very easy, that the intensity of the emission is much different. Here, we actually need to have an inset because our emission is this teeny-weeny little line on the side. So making this cavity really makes a difference. Also, to make sure that we have a cavity here, this is a cavity emission. If you shine a lot of off-resonant light onto this cavity, from all the, shall I say, lights that you light up in semiconductor material, this cavity will show itself to you where it is. In addition to this, this is our simulation, what we should see. And here we would expect something like 70% efficiency, while for this type of pillar, here exactly at the wavelength where we looked, we expect to see nothing. And I would say that this is quite in agreement with the simulation. So we have continued investigating this device. And of course, we looked at all the vital parameters that we will look at all the devices. So we have checked that the photon emission is still having 0 photon contribution. We have also measured time in entanglement and get a fidelity of 0.69, not 69, 0.69. And we also investigated if we do have any Purcell effects. So we're looking at many quantum dots that were resonant with the cavity and many that are not resonant with the cavity. And I have to tell you that this difference here exists not because we have a Purcell effect in the cavity, it exists there because the emission is suppressed at all the modes that are not resonant with. And last, but I would say very important piece of information, we have looked into collection efficiency, because this is why we started all this business, because we wanted to have high collection efficiency. And when we looked at all the relevant parameters, these 400,000 counts on the APD, the detectors, the coupling in the fiber, the optical losses, and the repetition rate, we get something like 70% in our 0.60. I can dance something. No problem. So we get nearly 70%. So what does this mean? It's a lot. So this result is, I would say, probably among 3 best that has ever been shown. The other 2 have used the so-called circular Bragg rating cavity or bullseye cavity. And well, I can tell you the main difference to the bullseye approach and our approach. We also have bullseyes. We try to work with bullseyes. They are fantastic devices, but you need to make 1,000 before one of them works. With us, if the raw material is good, so if the quantum dot will respond on the excitation, nearly all the devices work. And this is, I would say, far more scalable and far more useful for turning this into a, shall I say, technology. And last thing that I want to say, we have also simulated a little bit, can we make things better? If we change the number of dBrs on the bottom, or if we have a low index substrate, because we understood at a certain point that our beta might be higher, but with beta factor, you get the light in the cavity. It can go up, but it can also go down. And if you didn't do a good job on the bottom, then you're going to lose some light at the bottom. And if we change this a little bit, then we can get approximately over 2 nanometers, something that is larger than 80%. And this is, I would say, quite good. And now I'm going to completely change the story and tell you something about characterization of entanglement. Because as you can imagine, we are characterizing entanglement very often. We have a lot of devices that we need to check. And when it comes to characterization of entanglement, and here I'm really talking about determining the quantity of entanglement. So how much entanglement, not saying, oh, I have or I do not have entanglement, so yes, no answer, but say how much entanglement you have in the system. The only way how I know to do this is to perform full state tomography. And if we just have 2 qubits, 2 photonic qubits, that is 36 projective measurements that we have to do. And once you have this complete set of measurements, what you can do the reconstruction of the state, and this is usually done via maximum likelihood approach. And so if you want to measure less projections, and let us say if you have a larger number of qubits, the number of projective measurements will of course explode. If you want to use less measurements, first of all, you can't unless you make assumptions about the state. And if you use less measurement, your accuracy with which you can estimate entanglement will be significantly reduced, and it's not scalable. So our approach to this is deep neural networks. And so what we wanted to do were 3 things. We wanted to be able to accurately quantify entanglement using less than a complete set of measurements. That's the first thing that we wanted to do. Then we wanted to not need to know the state, so that we can quantify directly from the measurement data without the reconstruction. And the third thing is we wanted to have these neural networks be trained with the simulated data, because this significantly reduces the trouble of training them. And we have 2 approaches that we implemented, what we call the measurement specific, and that is when you know which measurements you're going to do a priori. So you know I'm not going to do 36 measurements, I'm going to do 18, and these are these 18. Or you do not know that a priori. This is measurement independent. Here, the neural network is a little bit different. The first layer is called volutional, and you give in together your measurement data and the description of the measurement. So let's see what we did. We have looked into 2 different quantifiers in 3 different cases. So this is here bipartite entanglement, and this is a 3-qubit entanglement. Here, for bipartite, we use concurrence.